Hey guys, welcome back to week 13 of Math 120. This is actually going to be the last video that we do for this class. We're coming up on the end of the semester, and I want to finish on the number one most important technique that we cover here at Math 120. It's a hypothesis test and a confidence interval for two different means from two different populations. I think that maybe more so than any of the other tests or techniques that we've talked about this semester, this particular test and confidence interval are the ones that you guys are most likely to use if you ever consume statistical literature or perform your own statistical tests later on in your lives or your careers. This is the big one. I think it's really the most useful, whether you're in social sciences or physical sciences or wet sciences. This sort of technique is one of the most useful. Unfortunately, it's pretty similar to something that we've already done before. We've already done hypothesis tests and confidence intervals for one mean. We already did those. So now we're doing a very similar techniques for two different populations. Everything that we do today is going to be about comparing two different populations. And in some sense, that's kind of the most natural question to ask about sample data. A lot of times when you're looking at a couple of groups, your number one question is there a difference? Does it seem like group one is different from group two? Is there evidence that one of the means is higher or lower or just not equals to? So I really think that if you only take one thing with you from this course, this is the most important one, and that's why I've decided to end it here on a bang. I hope you enjoy. Okay, first, the basics. I want to take a little bit of time to remember what you already know, because this new stuff that we're doing is just an extension of that. We've already talked about quantitative variables for a population, and you guys know all the details for that stuff. Remember, the first thing we need is a point estimate. What's a point estimate? A point estimate is a single numerical estimate for what we think is going on with the population. It's always a sample statistic. And the one that we use for mu, of course, is x bar. Makes sense. If we have to estimate the population mean, mu, we're going to do that with our sample mean, x bar. We also need to know something about the standard error. We know from the central limit theorem that these things follow normal distributions, but we still need to know how wide that distribution is. Is it a really fat distribution? Is it a narrow, skinny distribution? Depends on what's going on. That's what the standard error is all about. And you've seen, if we're talking about one mean for one population, the standard error for x bar is s divided by the square root of n. S is the standard deviation of our sample data, and n is the sample size. This is the same thing that you've used in your confidence intervals and your hypothesis tests for mu. Not proportions, means. Okay, so that's the technique that we've seen so far. Let's talk about the new one for two populations with two means. What happens there? If we've got two different populations, and we take a sample from each one, so we've got two different samples, then the thing that we want to think about is the difference between them. And maybe to keep this rooted in your mind, I think a really easy example is something like a medical trial. Like, imagine if there's a new pill or a new drug or something. When we test it, we need two groups. Got to have a control group that we can compare to. Those are the people who do not get the new drug. And a test group, the people who do receive this new medication. The whole point of a medical trial is to see, is there some sort of meaningful difference between these two? Does it seem like taking this new drug is changing something meaningful about whatever it is that we're measuring? Of course, this technique doesn't have to be used in a medical trial. I just think that's an easy example to think about in your head, because when they do medical trials, these hypothesis tests that we're talking about right now, this is actually how they make decisions about those. So we've got two populations. We're comparing their means. Of course, each population has to have its own mean for population 1, and the mean for population 2. We're going to call those mu1 and mu2, respectively, just the first mean and the second mean. So the thing that we really care about here is the difference between those means. In other words, mu1 minus mu2. All of our type tests and confidence intervals that we're going to do here are about that difference. Just like before, we need point estimates and standard errors to do anything. And I think they're pretty reasonable. First, for the point estimate, in other words, our educated guess about what the difference is, if we want to get a point estimate for mu1 minus mu2, then we're going to do the obvious thing. We're going to do the thing that you would guess. We've got two samples. We've got two sample averages. Let's find out the difference between them, literally, x bar 1 minus x bar 2. That's our point estimate here. And that's our first guess about how different these populations are. Of course, we're also going to need standard error. We know that our sample results aren't always going to be exactly correct every time. Sometimes it'll be bigger, sometimes it'll be smaller. What's that wiggle room? For the standard error, the formula is actually pretty similar to what it was before. Here I've got it typed out on the screen. I read that out loud as the square root of s1 squared over n1 plus s2 squared over n2. And I want to show you, it might be a little bit hard for you to read in text like this. If you want to see a pretty version of this, you can go to your textbook. I'll do that right now. Page 267. Here's page 267, which shows you the standard error for this stuff. Here's the kind of more mathematical typeset version of the same thing. If that helps you, you can take a look at this. Also, here in this section, you can look down and they've got some examples where they actually do this computation. Like here's one, for example. You can read through, look at the details, and that'll help you figure out what goes where. It's a pretty similar sort of thing. Here we have to add the two variances together and then take the square root. Once we've got these building blocks, we've got the point estimate, we've got the standard error, those two are enough for us to do all the neat stuff that we need to do. So let's try it out. Let's start with hypothesis tests first. Hype tests for two means. We've got two populations, two samples, and we want to see if there's some sort of difference between the population means. All hypothesis tests answer a question. And these tests answer this really natural and really important question. Is there evidence of a difference between these two groups? We know every time we take a sample, it's going to be a random sample, things can play out differently. Do we have strong evidence, statistically significant evidence, that there's some kind of difference between population 1 mean and population 2 mean? The actual tests have exactly the same strategy or structure as all of the other tests that we've done, same 4 pieces. There's got to be an hypothesis, or both of your hypotheses, null and alternate hypotheses. We're going to have a test statistic that looks pretty similar, a p-value that tells us how likely or unlikely this result is, and our final conclusion for what we actually think is going on in this population. Before we do an example, let's dive a little bit deeper into these things. First, the hypotheses, of course, the first step. These are actually kind of easier because if we're talking about tests for 2 populations, the null hypothesis is always the same for all of these things. Anytime we're doing a 2 means test, the null hypothesis is always the same. Specifically, we will always assume by default that there's no difference between the groups. That mu1 minus mu2 is equal to 0. This is always our null hypothesis for these things, which is kind of nice for you as a student. You don't have to really think about it very hard because you're always going to use this null hypothesis. We're going to assume no difference. Of course, the reason that we're performing this test is because we suspect that there is some sort of a difference. Remember, this is like innocent, but we're hoping to prove guilty. And for that alternate hypothesis, the claim that we're making, there are 3 possibilities. Maybe we think the difference is less than 0. In other words, mu1 is smaller. Or maybe we think mu1 is bigger, that the difference is positive. Or we might just think that they're different from each other, not equals to. Which one specifically we use is determined by the wording of the problem. In other words, what our claim or our suspicion is. You have to read the problem to see what are we testing for. That tells you what your alternate hypothesis is going to be. And that's really important because that tells you if you're talking about a 1-tail test or a 2-tail test. Changes the p-value, in other words. So you need to be really careful. Are you doing a 1-tail test, either on the left or the right, or are you doing a 2-tail test? You can see that from the wording of the problem. For the test statistic, this test statistic has exactly the same structure as all of the other ones we've looked at so far. Let me remind you, that structure here specifically, it's on top, observed minus expected, divided by the standard error in the bottom. Totally the same thing as for 1 mean and 1 proportion. But here, we're going to use all of the 2 means facts and plug them into the equation. This is a really great place to pause, by the way, and soak up all the stuff that's on this page. Just to make it clear, here, our observation is the point estimate. The actual difference that we observed is the first sample mean minus the second sample mean, x bar 1 minus x bar 2. Our expectation is the thing in the null hypothesis. And this one's kind of easy because for these tests, it's always 0. If we're doing a 2-mean test, we're always assuming by default that there's no difference. So we don't even really need to worry about the expected because it's just always 0. This thing right here is always 0 for these tests. And the standard error, or the denominator, that's the thing that we saw earlier a second ago that I showed you in your textbook. It's the square root of s1 squared over n1 plus s2 squared over n2. That's the first standard deviation is s1, and the second standard deviation is s2. If that seems a little bit weird, hang in there for a second. We're going to do an example, and I know it'll make sense. It's kind of a lot of notation. It's a lot to read, but trust me, it makes total sense once you do this. So all together, if we put those pieces together, our little Lego pieces, that means our test statistic looks like this. It's x bar 1 minus x bar 2 on the top, and on the bottom it's square root blah, 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 blah. Looks kind of nasty, but it's really not too bad. I'll show you here in a second. For the p-values, in short, it works basically the same. Use the t-table. You're going to get that test statistic. You're going to look it up in the t-table just like you did before. No difference here. There is one little issue. We've got 2 different samples here. We've got 2 different sample sizes. So what are we going to do for the degrees of freedom? Think about it. Before, for the degrees of freedom, it was n minus 1. But now that's not so clear because we've got 2 different sample sizes, right? We've got n1 from the first sample and n2 from the second sample. So which one are we going to use? There's kind of 2 answers to that question. There is a pretty complicated mathematical formula for finding out the exact degrees of freedom in this case. I am not going to torture you guys with that, especially since we're not in person. Instead, we're going to use a simpler version of this. It's an approximation, but it's not a terrible one. Just use the smaller of the 2. We've got these 2 different samples. If they're not the same thing, pick the smaller one and use that to find the degrees of freedom. Like, for example, if our first sample has a sample size of 34, and our second sample has a size of 43, then we're going to use that first sample. We'll use 34, and that gives me a degrees of freedom of 33, just as an example. Easy peasy, just use the smaller one. If you're using software to do these tests, there's an even better degrees of freedom and exact degrees of freedom, but it's kind of difficult to compute by hand, and I just don't want to worry about forcing you guys to do that. It's not terribly important. Lastly, in our conclusion, same as always. Works exactly the same as it does for all the other tests. If our p-value is small, then we're going to reject the null hypothesis, and that means we found evidence to support our claim. We're very happy. We've been vindicated. Our paper gets published. Yay! The end. On the other hand, if we get a large p-value, then that means we're going to fail to reject the null hypothesis. We didn't find enough evidence to support our claim, and we feel kind of sad, but that's the end. Okay, let's actually do one of these things so you guys can get a feel for how they work. I think once you see me do one, I hope you'll agree it's really not too tricky. It feels very similar to the ones you've done before. The formulas are a little bit grosser, but it's not a big deal. How about this example? First example, it's a hypothesis test for two means. A hungry math professor wonders, does Pizza Hut have a different average delivery time than Donato's? We're ordering a pizza, hoping it gets here fast, and we're wondering if there's evidence of a difference in average delivery time between the two pizza chains. To test this, she records data about her many pizza delivery orders. And here's the info. Over the 35 times that she ordered from Pizza Hut, she did the math and found out that the average delivery time was 24.3 minutes, standard deviation of 4.1 minutes. That's our first sample. That's sample one. For Donato's, she ordered Donato's 28 times. And from those deliveries, she found out that the average Donato's delivery time was 26.3 minutes with a standard deviation of 5.8. So the million-dollar question here is there statistically significant evidence to suggest that there is a difference in these mean delivery times? I mean, clearly there's a difference in our sample data. One of them is 24.3, one of them is 26.3, but maybe that's just due to random chance. Do we have statistically significant evidence that one of them is faster than the other? Well, let's do the test. We might not be saving lives here, but we're still answering a very important question. Oh, and I suppose before we answer that very important question, it's time for today's secret video question answer. Self-rescue. The answer for today's secret video question is self-rescue. This is a great book. It's got all sorts of awesome self-rescue diagrams for rope work if you ever get stuck when you're hanging off a cliff face. I suppose probably the best way to stay safe is just not to hang off of a cliff face in the first place. But if you're determined to do so, you really want to know how you can help yourself. So, self-rescue. Self-rescue. Okay, back to our test. Let's do this test. Before we really start the test, I want to take a second and collect all of the important information. I recommend that you guys do this too. There's kind of a lot of different there's two samples, so there's kind of a lot of numbers in this problem, and I like to take a second to really organize those things and make sure I understand what everything is. Here, I'm going to let Pizza Hut be sample 1 and Donato's be sample 2. It doesn't matter which one's which, as long as you're consistent throughout the problem. If you really want Donato's to be sample 1 and Pizza Hut to be sample 2, you can do that. Just make sure you're consistent when you plug in the numbers from the different samples. So here, my first sample size, that's Pizza Hut. There were 35 Pizza Hut deliveries. The average for Pizza Hut was 24.3, and the standard deviation for Pizza Hut was 4.1. For Donato's, sample size for Donato's was 28. The average delivery time for those was 26.3 minutes. And the standard deviation for those was 5.8 minutes. Okay, now that we've got everything straightened out, it's pretty easy for us to plug and chug and do the test. Let's do it. First, for the hypotheses, the null hypothesis is always mu1 minus mu2 equals 0 for these tests. Always. This thing right here. So that's nice. We don't have to worry about this. Difference is 0. For our alternate hypothesis, we do need to think about this a little bit. And this comes from the wording of the problem. The key thing that tells me that this is a two-tailed test is that word right there, differ. We're not testing to see if it's greater than or less than. We're looking for a difference. In other words, not equals to. So that gives me a not equals to right there. All right, so let's find our test statistic. I'm going to use the same formula that was up above. If you forgot, you can go back and remind yourself. I'm just going to plug everything in to find our test statistic. Here, that's x bar 1 minus x bar 2. In the denominator, that's the first standard deviation squared over the first sample size, and then the second standard deviation squared over the second sample size. And, oh, what the heck, what is this? I'm going to run my code, and I get a test statistic of negative 1.54. So that's the thing we're going to look up. 1.54 in the table, in the t-table. The t-table only has the positive side of the distribution, but that doesn't matter because it's symmetric on both sides. So let's look this thing up, and I know we're doing a two-tail test. So I'll know how to find the p-value. We need a degrees of freedom for this stuff. And I'm going to use the smaller of the two sample sizes. Remember, Pizza Hut was sample size 35. Donato's was sample size 28. Here, we're going to use the smaller one. 28 minus 1 is 27. That tells me where I'm going to look on the table. So our test statistic is 1.54. Degrees of freedom is 27. Let's go over to the table. It's at the very end. Just find it by scrolling. Yeah, there we go. Looking at the t-table. All right, here we go. Degrees of freedom was 27. Our degrees of freedom is 27. That's at the bottom here. My test statistic was 1.4 something, so that's between here and here, right? That's where my test statistic lives, somewhere between these two. So I'm going to look up at the top margins here to get the p-value. My p-value is going to be between 0.2 and 0.1, somewhere between those two right there. Let me talk through that one more time before I continue. We got a test statistic of 1.54. My degrees of freedom is 27. So I'm matching those up on the table. Degrees of freedom is 27. My test is, can you see my little mouse cursor there? I'm moving it back and forth. Our test statistic lives between those two. So my p-value up here has to be between 0.1 and 0.2. Remember, this is a two-tail test because of not equals to. So I'm looking at the two-tail p-value. Thus, our p-value is between 0.1 and 0.2. All right, so we've got our evidence. Let's make the conclusion. We've got a large p-value here. Here, p is bigger than 0.05. Remember, alpha equals 0.05 is our default significance level. We got a large p-value, so we fail to reject the null hypothesis. We got a large p-value, fail to reject the null hypothesis. That means we did not find evidence to support the alternate hypothesis. here. We did not find evidence to support the alternate hypothesis. Now, what does that mean? It means we didn't find evidence to suggest that there's a difference between the two populations. There's not enough evidence to conclude that there's a difference in mean delivery times between the two pizza chains. The end. Clearly, we observed a sample difference, but seems like that was explainable by random chance. There's no strong statistical evidence to suggest that Pizza Hut is doing better than Donato's in this case. And that's it. That's the test. Pizza delivery might be kind of a silly example, but this is a powerful technique anytime you want to compare two groups, whether it's a medical test or some other kind of research. If you want to see, are these two things different? This is the test you use to do it. Okay, one more thing. Still got to do confidence intervals. Let's talk about confidence intervals for two means. Remember, confidence intervals are all about estimating a population parameter. So here, specifically, when we make a confidence interval for two means, we're estimating the difference in the means. That's what this estimate is all about. How different are they? What range of values could that difference occupy? That's what the confidence interval estimates. Not yes or no, is there a difference, but maybe even better, how different are they? Think about the pizza delivery time. Does it seem like there's a minute difference, 2 minutes difference, 5 minutes difference, no minutes difference? That's what this confidence interval is going to tell us. And let me remind you guys, we've done a few confidence intervals already. They all have exactly the same format. They start with a point estimate in the middle, then plus or minus to get the two sides, the margin of error on either side. That's got both a critical value, it's going to be t here, and the standard error, that's the square root of blah, 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 like you saw before. So if we put it all together using our point estimate and standard error for two means, here is the formula for the confidence interval. Might look like a mess at first, but it's really not too bad to use. The t critical value is exactly the same as our ones before. I'll show you again if you forgot how to find those. Easy peasy, plug and chug. Okay, let's do an example. To keep things simple, let's do an example with exactly the same sample data that we thought about before. Let's use that pizza delivery data and make a confidence interval to estimate the difference in delivery times. So I've already copy-pasted the data. This is exactly the same stuff before. We've got 35 deliveries from Pizza Hut, 28 deliveries from Donato's. We're going to estimate the difference in mean delivery time. How different does it seem the delivery times are? So one other thing too, we're estimating this difference with a 95% confidence interval. I'm choosing 95%. It's pretty standard. We could do 99%. We could do 90%. Let's do a 95% interval here. Now, in this formula, let me just remind you, here's the formula that we're about to use. We already know all of that stuff. The only thing that we don't know is the critical value, t. That's the only piece of information the problem doesn't directly give us. We need to find the critical value. Remember how this goes. My head is the curve. My head is the curve. We've got 95% of it in the middle. And that means the leftover for the two tails, they've each got 2.5%. 2.5% of each of those, so that's 5% total for the two tails, 95% in the middle, and we've got everything accounted for. So we're going to go to the t-table, and we're going to look up 0.025 on the one tail. That's the same thing as 0.05 for the two tail. And just like before, I'm going to use degrees of freedom 27 because our smaller sample size was 28. Okay, let's go look at the table. We've got degrees of freedom 27. I'm looking 0.025. Degrees of freedom is 27 here, so I'm looking at this row. Looking down there. And my one tail area is here, 0.025. Notice it totally doesn't matter which way you think about it. Each of the individual tails have 0.025. The two of them together have 0.05. So those are exactly the same column. And when we match it up here at the bottom, there is the critical value that we're looking for, 2.05. That's my critical value. Just to talk through that again, I found the degrees of freedom, I found the tail area on the top, and I matched those to get 2.05. So here we've got t equals 2.05. All right, let's stick that in. I'm going to just copy paste real quick my summary so that it's easy for me to remember all the important information. So let's plug and chug. I'm using the confidence interval formula that we saw up earlier. First, I've got x bar 1 minus x bar 2. That's 24.3 minus 26.3. We need to do both the plus and the minus. I'm going to do the minus first. We just found out that our t critical value is 2.05. So let's get that in there, 2.05. And now I need the standard error, square root of 4.1 squared over 35. That's the first standard deviation squared divided by the first sample size. Then 5.8 squared for the second one divided by 28, second sample size. That gives me a lower bound of negative 4.65. And for the upper bound, upper bound is going to be exactly the same, except I'm going to do a plus. That gives me an upper bound of 0.65. Now hold on, let's make sure we understand exactly what these mean. In other words, we're 95% confident that the true difference in mean delivery time is between negative 4.7, I'll just round it off, negative 4.7 minutes and 0.7 minutes. We've estimated the difference in delivery time. We think that difference has to be somewhere between, at the most, negative 5 minutes, like at the most 5 minutes off. And on the other side, about positive 0.7 minutes or positive 1 minute. This might seem kind of weird. Maybe think about it this way. Notice that it's possible that the difference in mean delivery time is 0. Think about that. Imagine we've got this number line. We've got this number line. Here's my confidence interval. There's a picture of my confidence interval. On the one side, it could be mu1 minus mu2 equals negative 4.7. And over on the other side, it could be mu1 minus mu2 equals positive 0.7. Whatever the actual difference is, we're 95% confident that it's somewhere in there. So maybe visually it makes sense. Maybe 0 is like right about here where I'm highlighting, just to eyeball it. It's totally possible that the difference is 0, i.e., it's possible that there's no difference. And that's exactly what our hypothesis test said. Think about it. What was the null hypothesis for the hypothesis test? The null hypothesis was mu1 minus mu2 equals 0. And we failed to reject that null hypothesis. This confidence interval is telling us exactly the same thing. It's saying it's possible that the difference is 0. That's somewhere in here. So maybe there's not a difference at all. This agrees with our hype test, where we failed to reject the H naught, that mu1 minus mu2 is equal to 0. The confidence interval says the same thing. It's possible that the difference is 0. I think that's really interesting. That's the first time we've really thought about that in this class. Confidence intervals and hypothesis tests are actually just two different versions of the same technique. To think about it in other language that we've used, hypothesis tests are forwards problems. We've got an observation, and we compute the probability based on that. That's the p-value. On the other hand, confidence intervals are backwards problems. Confidence intervals are backwards problems. We have a particular region in mind, the middle 95%, and we want to figure out what those cutoffs are. But they're kind of just two different versions of the same thing. Whether you're going forwards or backwards, you'll always get the same results. And this technique, it's not just an accident here that we got the same conclusion. It's always the case that confidence intervals and hypothesis tests give you the same conclusion about a population. They just do it in two different ways. Confidence intervals estimate what's going on with the population, and hypothesis tests answer a question about what could be going on with the population. I think it's kind of interesting. They might seem totally different, but they're actually just two different sides of the same coin, forwards and backwards. And that's why we teach them both. That's why they're both really common techniques in statistical analysis. Generally speaking, when people mean statistical analysis, they're talking about either a confidence interval or a hypothesis test. And I hope that our discussions over the past week, I know it hasn't been ideal because we've been away and it's harder to learn remotely, but I hope that these videos have helped give you some sort of feel for the basics of that process and what the important considerations are. Whenever you hear about some sort of statistical conclusion in the news or in a study or something like that, I hope you can think a little bit about the underlying mechanics of those things. What sort of confidence interval was used? What sort of hypothesis test was used? And was there some kind of error in those? Did we make a false positive? Did we make a false negative? What sort of implications might that have for the human beings involved in making a decision about that data? I think that's really cool. And I hope you've enjoyed thinking about it with me too. This video is the last new material we're going to do in this class. I think there's nothing more important than this specific technique, the two means technique. So let's stop there. The quiz is going to have predictable stuff. There's going to be a confidence interval for 2 samples and a hypothesis test for 2 samples. I'll put some practice problems up for you and the solutions as usual. As always, if you guys have questions about this stuff, I'm happy to just hang out and geek out on Google Hangouts. I can make up examples. I can explain anything that happened here. Remember that these notes are available on my website. So I will see you out there, guys. Good luck with everything in this very strange time. I hope you're well. I hope you're safe. And I wish the best.